Okay, this is the last problem I'm going to work for you guys, so I hope you're paying attention. The problem reads, a toy balloon filled with air has an internal pressure of 1.25 atmospheres and a volume of 2.50 liters. If I take the balloon to the bottom of the ocean where the pressure is 95 atmospheres, what will the new volume of the balloon be? And how many moles of gas does the balloon hold? Assume that our temperature is 285 Kelvin. So this is another two-part problem, and we can treat it into separate parts. First thing we always do is write our knowns and our unknowns. What do we know? We know that our initial pressure is 1.25 atmospheres. Our initial volume is 2.50 liters. At the bottom of the ocean, our final pressure is 95 atmospheres, and we're looking for our final volume. We can use Boyle's law rather than starting with the combined gas law. We do have a change going on, so we could use the combined gas law. P1V1 equals over N1T1 equals P2V2 over N2T2. And because our temperature is constant, that would cancel out. And we assume our moles of gas are constant. Nothing's moving in or out of the balloon, so those cancel out because N1 equals N2 and T1 equals T2. So we're left with Boyle's law, P1V1 equals P2V2. And if we're looking for V2, then we need to rearrange our equation to give ourselves V2 isolated by itself on one side. We divide both sides by P2 and we get P1V1 over P2 equals V2. And now we can go ahead and plug stuff in. V2 equals P1, 1.25 atmospheres, times V1, 2.50 liters, over P2, 95 atmospheres. Okay. We plug everything in. 1.25 times 2.5 divided by 95, and we get 0.0328 liters is our final volume. That is a lot of shrinking when we get to the bottom of the ocean. Now we can go and do part B. How many moles of gas does a balloon hold? Okay. We have known and unknowns. We know we're looking for the moles of gas, and we know that number is not going to change. So we don't have to use N1 or N2. We know a P1, a P2, a V1, and a V2, so we can write those down. And we know a temperature, and we always know R. 0.0821 liters atmospheres per mole Kelvin. Let's see, 285 Kelvin. So now the question we ask ourselves is, do we plug in our initial values or our final values? And guess what? It doesn't matter. If we plug either of them in, we should get the same thing, as long as we don't mix and match. We have to use the initial values for both pressure and volume, or the final values for both pressure and volume, but we can't use initial pressure and final volume, or initial volume and final pressure. But as long as what we plug in is the same, initial or final, for every value, we're fine. So the next question is, what are we asking ourselves? The number of moles of gas is not changing. What equation are we going to use? If there is no change, then we use our ideal gas law. Even though we have all these final and initial numbers, we don't want to use our combined gas law, P1 over P1 V1 equals. We don't want to use the combined gas law, P1 and V1 over N1 T1 equals P2 V2 over N2 T2, because our number of moles are constant, and they will end up canceling out of the equation, which means we won't actually be able to solve for what we're looking for. So instead of using the combined gas law, we're going to pick some values and use the ideal gas law. Which values do we pick? Again, doesn't matter, and to prove it to you, I'm going to use both. So we're looking for moles. First, I rearrange the equation to isolate moles, get moles by themselves on one side. We do that by dividing both sides by RT. And now I'm going to try using P1 and V1 first, because they're first. So N equals P1 is 1.25 atmospheres, V1 is 2.5 liters, over R is 0.0821 liter atmosphere per mole Kelvin, and T is 285 Kelvin. That's a constant. When we do 1.25 times 2.5 over 0.0821 over 285, we end up with 0.1336 moles, and we have to double check that we got this right by checking that our units cancel. Atmospheres cancel with atmospheres, liters cancel with liters, Kelvin cancel with Kelvin. We're left with moles. And by left with moles, I mean we're left with 1 over mole, which is the same thing as 1 divided by 1 over mole, which is the same thing as 1 times mole over 1, which is the same thing as moles. So we know that this unit is correct, and that means we plugged everything in. Let's try solving it again with P2 and D2 and see if we get the same answer, or mostly the same answer. If anything changes just a tiny bit, then it's probably just because we rounded differently somewhere. So if we plug in P2, 95 atmospheres, and V2, 0.0328 liters, which we just calculated, divided by 0.0821 liters atmospheres per mole Kelvin, times our temperature, which didn't change, 285 Kelvin. Plugging all that in and calculating it, we get 95 times 0.0328 divided by 285 divided by 0.0821, and we get 0.1332 moles, and that is a very close number to 0.1336, which is how we know that we did it right. The reason this is a 2 and this is a 6 is probably just because of where we rounded this number right here when we solved for it in part A. So that was another two-step problem. There were 2 ways you could have solved it. Either one is equally valid, but you need to show me on the test which one you choose to do. If there's a problem like this on the test, hint, hint, you need to show me using either the first values or the final values. That's it. Come in for questions on Monday morning if you have them. I'll be there. Otherwise, good luck.